Okay, hey everyone. Welcome back to our series on linear algebra. This is section 3.3, part 2. So we're just going to finish up talking about matrix inverses. So last time we finished off with the definition of an elementary matrix. Today, we're just going to finish up with the fundamental theorem of invertible matrices. So this is actually version 1. Okay, first of all, you've heard of the fundamental theorem of calculus, and you may have heard of the fundamental theorem of algebra. These are statements that are so important that we say that they're like the most important theorem in the subject or whatever. So today we're going to be talking about that for matrices, invertible matrices. The theorem goes like, okay, this is version 1 of that theorem. We're actually going to talk about version 2 in the next video. That'll be kind of how we finish off the next video. It's, well, notice it's a long list of 5 things. Let's talk about them. So the fundamental theorem of invertible matrices says, suppose A is an n by n matrix. Then we write TFAE. That is shorthand for the following are equivalent. What that means is if you know one of them is true, you know all of them are true. And if you know one of them is false, then you know all of them are false. So this is a brief characterization of what an invertible matrix is. So the first one is A is invertible. That is true if and only if the system AX equals B has a unique solution for every single B, like every single vector B in R. That's true if and only if AX equals 0, the homogeneous system, has only the trivial solution, or the reduced row echelon form of A is the identity, or A is a product of elementary matrices. These are all equivalent. These are all equivalent, like logically equivalent statements to the statement that A is invertible. And next time we're actually going to like double the length of this list, and then some. So yeah, stay tuned for that one. But for now, I want to show you what the proof looks like. It's kind of cool. Essentially, so before we've talked about if and only if proofs. You have to prove like, oh, each one implies the other one. So actually, we're not going to do quite that. We're going to do a circular chain of implications. It'll go like this. 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, and 5 implies 1. Now, if you know that any one is true, you can just imply the rest all the way to whichever other one you want to be true. So that's how we're going to do it. So it goes like this. We start by assume A is invertible. Well, we'll do it like this. I'm going to do this mostly verbally. So 1 implies 2. So we're going to assume that A is invertible, and we want to prove that AX equals B has a unique solution for every B inside of R, or Rn. Well, last time we had a theorem that said precisely that statement. If A is an invertible matrix, then X equals A inverse B is the unique solution. Honestly, you could also just multiply both sides on the left by A inverse, and you'll arrive at a unique solution. Okay, so there we have it. Now we want to do 2 implies 3. This is also pretty brief. Well, okay, if AX equals B has a unique solution for every B in Rn, 0 is a vector in Rn, and the 0 vector is also a solution to this equation. But by the assumption in number 2, assuming number 2 to be true, the 0 vector has to be the unique solution. So, okay, I'll just say direct. B equals 0. Something like this. For 3 implies 4, this is interesting. Supposing that ax equals 0 has only the trivial solution, then we want to prove that the reduced row echelon form of A is the identity. So let's write out A. It's going to be little a 1, 1, a 2, 1, all the way down to a n 1. We're assuming a is n by n, right? We'll go all the way over to a 1n, all the way to, a n n, and so on. Okay, this is shorthand for writing all the entries in the matrix. But then we're going to augment with the 0 vector. And then we're going to row reduce. But the thing is, if we view this as the augmented system for a homogeneous system, the augmented matrix for a homogeneous system, then we know what this row reduces to. It has only the unique solution. So we can just skip to the row reduction, which looks like this. Well, after we won't even do the row reduction. You know what will happen. We'll have 1s on the main diagonal, and any row operations done on the 0 vector will remain the 0 vector. And so the system of equations is going to be x1 equals 0, x2 equals 0, all the way up to xn equals 0. But what is the augmented matrix for this system? It's the identity, right? And so we have, well, we'll just leave it there. It's the identity matrix. In other words, there are no free variables in this system, right? If there were, it would contradict the assumption that the trivial solution is the only solution to the system of equations. Great. Okay, and so then 4 implies 5. We want to assume that the reduced row echelon form of A is the identity. And we want to prove that A is the product of elementary matrices. Well, there's a sequence of row operations taking A to in, sure. Each row operation corresponds to an elementary matrix. Left multiplication by an elementary matrix. I'm going to write that EI, elementary. Okay, so each row operation is left multiplication by some elementary matrix. In other words, the identity is you take A, then multiply by E1. That will be the first row operation. Then E2, all the way up to EK. In that order. You do them in that order. Each one is a row operation. You just do, like this, associative property. That will row reduce A to the identity matrix. But then what we do is we call this sequence, this product of elementary matrices, called this B. Okay. And now we just have to ask, well, this means that BA is the identity. Yeah. But then what we ask is just invert both sides of this equation. The inverse of the identity is the identity. You can check that just from the definition. But this is also by previous theorem. This is A inverse, B inverse. But B inverse is just the reversed sequence of row operations. Reversed and inverted. So it'll be the opposite order and everything raised to the -1. All the way up to ek. But this thing, still the identity, if we multiply it on the left by a, then a is a inverse times, all the other stuff. A times A inverse is the identity. And so we're left with E1 inverse, E2 inverse, all the way up to EK inverse. But the very last theorem that we had from last time tells us that each of these inverted elementary matrices is itself an elementary matrix of the same type. And so there we have A is a product of elementary matrices. Okay? And by the way, 5 implies 1 says that, well, each of these matrices, if A is a product of invertible matrices, well, of elementary matrices, each elementary matrix is invertible. And the product of invertible matrices is invertible, right? And so product is invertible. But 5 implies 1, 1 implies 2, 2 implies 3, and so on. So we're done. These are all equivalent statements. It's kind of a long proof, but it's really nice. And by the way, it gets a lot longer. So we'll see more next time. So we want to express, okay, but we need to do some more work with elementary matrices. So we're going to express this matrix A, 1, 3, 5, 7 as a product of elementary matrices. First thing we should do is row reduce, right? So we'll take row 2 minus 5 row 1. It'll be 1, 3, 0, 7 minus 15, -8. Then we'll do -1/8 row 2. 1, 3, 0, 1. And then the last thing we just need to do is row 1 minus 3 row 2. And we're left with 1, 0, 0, 1, the identity. Each of these row operations can be expressed as an elementary matrix, right? So the first row operation, remember we have to do these, in order. So the way that I like to do this is I put the identity is A. We have 3 row operations, so we'll just E1, E2, E3. The first row operation will have elementary matrix. Well, what do? We take 5 row 1 and subtract it from row 2 of the identity. So 5 row 1 is -5, 0, subtracted from the second row. Leave the first row the same. We're looking at this elementary matrix. The second one, E2, is -8 row 2, -1/8. So 1, 0, 0, minus 1/8. And the third one is row 1 minus 3 row 2. So E3, just do that to the identity. We get 1, negative 3, 0, 1. So the identity is, the identity, let me put this over here still. Actually, well, yeah. I won't write it out. The identity is A times E1, E2, E3, going backwards, right? Which means that A we have to multiply both sides on the right by E3 inverse, on the left by E3 inverse, then on the left by E2 inverse, and then on the left by E1 inverse. So that A, I want to make sure that I have enough space for this, is E3 inverse, E2 inverse, E1 inverse, multiplied in that order. Except I've written the wrong order. These are all left multiplications. So E1, E3 inverse, E2 inverse, E1 inverse. Right? If I multiply both sides on the left by E3 inverse, and then on the left by E2 inverse, and so on, I'm gradually pulling them over across the equal sign. To finish the job, we just need to write down what these matrices are. Right, so E1 inverse, here we go. First of all, we don't need to check invertibility for all of these because they're elementary matrices, they're invertible. Their inverses, well, let's compute them using the formula for inverse of a 2x2 matrix. Seems like the easiest way. You'll find it's the opposite. Well, anyway, okay. So we have to do, okay. AD minus BC, if you remember that from the last video, is 1 minus negative 5, minus 0 is 1. Then we have to switch AD and negate BC. Right? And notice, okay, what is the opposite of subtracting 5 copies of row 1 from row 2? That would be adding 5 copies of row 1 to row 2. Right? Is the opposite row operation. Maybe an easier one, this is inverse. Maybe an easier one to see is E2 inverse. Well, what did we do? We just scaled the second row by a factor of negative 1/8. Probably the opposite of that would be scaling up by a factor of 8. And sure enough, AD minus BC is 1 times negative 1/8, which is negative 1/8, minus 0, still negative 1/8. So we have to do 1 over negative 1/8 times, flip the order, negative 1/8 and 1, and then negate the off diagonals, 0, 0. But 1 over negative 1/8 is just negative 8. And if you scale this matrix by a factor of negative 8, the zeros stay zeros. Negative 8 times negative 1/8 is 1. And negative 8 times 1 is negative 8. And so E2 is just this, do the opposite matrix. Okay, E3 inverse. Last one. You can pretty much guess what this is going to be. We'll compute anyway. AD minus BC is 1 minus 0, which is 1, times, flip the main diagonal, nice, and then negate the off diagonals. We're done. Plug into this formula. You should also probably actually do the matrix multiplication to check to make sure that we got the matrix A back. I'm going to omit that step here. Okay. So now we have a really convenient consequence of that fundamental theorem of invertible matrices, which is that we actually don't need to check both properties of the inverse matrix. In fact, we can just check like one of them. Like for example, if you have two matrices, if A is a square matrix and B satisfies either one of the two-sided products, either AB is equal to I or BA is equal to I, you can stop checking. Then B is the inverse of A, and A is invertible. Right? So let's check that. So we start with, suppose that B times A. We'll do one case. So we have to prove this theorem once for each of these. We're going to do the BA and not the AB. So suppose that BA is equal to I, the identity. And then we just look at the equation, the homogeneous system of equations, AX equals 0. Well, just multiply both sides of this equation on the left by B. That's a matrix equation, right? It's a product of a matrix and a vector, and it's equal to the 0 vector. We can multiply both sides by B. So BA x is equal to B times 0. But BA, by assumption, that's the identity. That's just IX. Oh, but the identity times anything is itself. So this is just X, okay? And what is B times the 0 vector? Well, anything times the 0 vector is the 0 vector. In other words, the unique solution to this system of equations is just the 0 vector. But by the fundamental theorem that we just proved, this means that A is invertible, right? A inverse exists. Like by 3 implies 1. A inverse exists, right? But then if A inverse exists, then I can multiply both sides on the right by it, both sides of this equation. A inverse is I inverse. I A inverse. Okay, but we're about to multiply a lot by the identity. I times anything is itself. And this guy is the identity. In other words, B is A inverse. And you could do exactly the same line of reasoning. It's just that the only difference is like, if you wanted to do AB is I, then you have to multiply on the right. Right, so anyway. So the last thing that we're going to end with is how to compute the inverse of a matrix. This is theorem 3.14. Okay, sorry, this is math class. I had to make the joke. Okay, so let A be a square matrix. So if you have a sequence of row operations that takes A to the identity, then you have to ask, what does that sequence of row operations do to the identity? And the answer is it takes it precisely to the inverse. Okay. So again, this proof technique is very similar to the one that we did for 4 implies 5. Essentially, if I have the sequence I'll just write EK all the way down to E2, E1 equals times A equals the identity. We just let B be this product. Okay. Well, by the theorem that we just proved, BA equals I. Right? The sequence of row operations whose elementary matrices are E1 through EK, takes A to the identity, well, then the product of all of those elementary matrices together is a matrix. And that matrix, when multiplied by A, is just the identity. That's just the associative property, right? And so, by the previous theorem, B equals A inverse, right? Now the question is, what does that sequence of elementary matrices do to the identity? Well, actually, almost already have it. If we do EK all the way down to E1 times the identity, this is B times the identity, which is B, which is A inverse. It's not surprising. All I did was ask, what is B? We just had to say it again, right? We just have to say it like, if we did that thing to the identity, then at the end of that row reduction process, we're looking at A inverse. Okay, and that is actually just the proof. It's kind of very strange. It's just like is. No. It's a consequence of the previous theorem that we proved. Now, so we're left with this example. Find the inverse of A, which is this matrix. And the strategy that we're going to employ is kind of amazing. Row reduce A augmented with I reduce A, so assuming that A is invertible, which we're going to have to just assume for now, we want to row reduce A down to the identity, and then simultaneously we're going to row reduce the identity, and it will row reduce down up to A inverse, right? It's just a consequence of the previous theorem. We just do the row reduction simultaneously, right? Instead of keeping track of what we're doing to A and then going and doing that to I, we just make a gnarly n by 2n matrix and row reduce that thing. So let's go. It goes like this. Okay, duplicate. So this is probably the most intense row reduction you're going to see me do live. 3 by 3 matrix. Let's go. I haven't worked this one out before recording, so this is truly live. Okay, let's hope we don't make any computational errors. The first thing that we'll do, I see a 1 here, so we'll pivot around that 1 and subtract. I'm going to do the first 2 row operations at the same time. We'll do row 2 minus 2 row 1 and row 3 minus 1 row 1. That will give us 1, 2, negative 1, 1, 0, 0. We'll have a column of zeros. We also will have negative 2 and negative 1. And the rest of the identity matrix will be the same. And then in these spots, negative 2 times 2 is negative 4, plus 2 is negative 2. Jeez. Positive 2 plus 4 is positive 6. Okay, negative 2 plus 3 is 1. And positive 1 minus 3 is negative 2. I'm going to check on that one. No, I'm not. I don't have the book open. Okay, well. Okay, it's probably right. If this doesn't reach the identity, we're doomed, but it'll be okay. I think that we can comfortably, actually, while we're here, I'm going to add a third step. which is take 1/2 of row 2. Negative 1/2 row 2. So that'll give us a positive 1 that we can pivot around. And negative 3, a positive 1, and a negative 1/2. Okay, here we go. 3 row operations all at once. That was exciting. Now we'll pivot around this 1. So row 3 minus row 2. The first row will stay completely the same. The second row will also stay the same. The third row, take the negative of the second row and add it to it. You'll get a 0 here. You'll get a 1 here. That's convenient. You'll get negative 2 down here. Negative 1/2 is 1/2 plus 0 is positive 1/2. And then 0 plus 1 is just 0. It's just 1. Double check that one. Oh no, we're good. Okay, it's correct. Great. I'm gonna do the last ones all at the same time, I guess. Right, now we just, oh no, we can't do this. Okay, well, in that case, we'll just clear out this cup. Want to do that one first? No, let's clear out this guy first. Okay, so that means we'll take row 1 minus plus row 3. Sorry, row 1 plus row 3, and row 1 plus 3 row 3. One, 0, 0, 2, 1, 0, 0, 0, 1. Okay, now I got to do some serious work. Okay, take 3 times row 3. Oh, should be row 2. That's very important. Okay, take 1 times row 3 and add it to row 1. So 1 minus 2 is negative 1, 1/2, 1. Then take 3 times row 3 and add it to row 2. So negative 6 plus 1 is negative 5. 3/2 minus 1/2 is 2/2, which is 1. And 3 plus 0 is 3. We got there. Okay. Negative 2, 1/2, 1. And then our last step, we can just clear out that 2 above that 1. So what is that? Row 1 minus 2 row 2. 1, 0. Oh, we know what the left-hand matrix is going to be. We're to the identity now. 0, 1, 0, 0, 0, 1. And on the right, we take 2 copies of the middle row, make them negative, and add them to the first row. The bottom row will stay the same. Negative 2, 1/2, 1. The middle row will also stay the same. Negative 5, 1, 3. And then negative 2 copies of the middle row is negative 10 minus 1 is positive 10 minus 1, which is 9. Negative 2 plus 1/2 is negative 3/2. And negative 6 plus 1 is negative 5. Thus, oh man, A inverse is 9, negative 5, negative 2, negative 3/2, 1, 1/2, -5, 3, 1. And to finish out this video, I'll do a magic trick. No, I'm just kidding. I'm just going to multiply the matrices on one side, and we'll hope that we get the identity. If not, I have no idea what we're going to do. So here's A. Here's A inverse, scaled to size. Okay, what do we got? 9 minus 10 plus 2 is 1. That's promising. I'm going to go straight down. So 18 minus 10 minus 8 is 0. 9 minus 15 plus 6, also 0. Okay, here we go. -3/2 plus 2 minus 1/2, 0. Okay. -3 plus 2 plus another 2, 1. Okay. -3 plus 3, sorry, -3/2 plus 3 minus 3/2, 0. -5 plus 6 minus 1, 0. -10 plus 6 plus 4, 0. And -5 plus 9 minus 3, 1. We did it. That is a really good place to stop this video. I will see you guys in the next one.